Okay, let me welcome everybody back to another session of organic chemistry. In today's session, we are going to continue with the discussion on Chapter 20. Chapter 20 is concerned with the chemistry of carboxylic acid and nitriles. One announcement to make. I did post the Spring 2012 end of Chapter 20 review in Blackboard for those of you who might want to take advantage of that. Keeping in mind that the homework assignment is due on Sunday, that is March 23rd at 11 p.m. So you may want to review that video, so it gives you some idea how to approach some of the questions in that assignment. Okay, when we left on Tuesday, we were discussing the synthesis of carboxylic acid. So what I want to do today is to continue with that discussion. Okay, I believe when we left, I gave you, with regard to synthesis of carboxylic acid, I gave you 4 methods, right? Okay, so this will be method number 5. This is method number 5. So we will call this oxidation, potassium permanganate oxidation of alkyl benzene. And of course, we have done this before. Anytime you have an alkyl group attached to benzene, the benzene structure, and you take potassium permanganate, potassium permanganate will oxidize the carbon that is attached to the benzene ring to carboxylic acid. Say, for example, just to give you a couple more examples here, if we have this, it does not matter how long the alkyl group is. If you have this, and you take potassium permanganate, generally we do this reaction under acidic conditions. All of this here, all of this carbon here, will be converted to carbon dioxide, except for the carbon that is attached to the benzene ring, and that will be converted to a carboxyl group. So you are going to get this. Supposing you have this molecule here, if you have this, okay, this molecule also will be oxidized by potassium permanganate in acidic medium. This carbon here becomes a carboxyl group, and this carbon here becomes the carbon of the carboxyl group, and this carbon here will be gone as carbon dioxide. Okay, so in that case you are going to end up with a dicarboxyl acid. It does not matter what kind of alkyl group you have attached to the benzene ring. Everything will be converted to carbon dioxide except for the carbon that is attached to the benzene ring and that carbon will be converted to a carboxyl group. Okay, so this is another method for making carboxylic acid. Now, method number 6, everybody got this? Okay, method number 6, still under synthesis of carboxylic acid. We've done this also before, so this should be reviewed to all of you. This is potassium permanganate oxidative cleavage of carbon-carbon double bond. Okay. So let us call this method number 6. Okay. So if you have a carbon-carbon double bond, just like here, what will happen here with potassium permanganate, you are going to cleave this right here, and each one of these carbon here, as long as the carbon is attached to an hydrogen atom, that carbon will be converted to a carboxyl group. Okay, and therefore in this case you get this product here. Let me give you a couple more examples. Supposing we have this. If I have this here, and I react this with potassium permanganate, what happens here, of course, we are going to cleave this right here. This carbon that is attached to an hydrogen becomes the carbon of a carboxyl group, and this carbon here, which has no hydrogen attached to it, becomes the carbon of a ketone. Okay? So we are going to get this. Okay, so we have this carbon here is now this carbon, and this carbon here is now this carbon. So this is another method for making a carboxylic acid, oxidation of a carbon-carbon double bond. Another example. Okay, if I take this here, and I react that with potassium permanganate, in this case, this is a terminal alkane. Okay, you are going to cleave this. This carbon becomes the carbon of a carboxyl group, and this carbon here, because we are now dealing with a terminal alkene, this becomes carbon dioxide. So you will get this product here. Okay, so now so far we have given you 6 different methods for making carboxylic acid. So at this point, what I want to do now, we want to go to the reactions of nitriles and carboxylic acid. Okay, keep in mind, before we left last on Tuesday, I gave you 3 methods for making nitriles, And now I have given you 6 methods for making carboxylic acid. Okay, so now let us go to reactions of carboxylic acid and nitriles. Okay, so what I want to do, I want to start with the reactions of nitriles, because we don't have too many of those. Reactions of nitriles. So I will say 1. Hydrolysis of nitriles to give carboxylic acid. We've seen that before, right? So that is just a repeat of what we did when we did the synthesis of carboxylic acid. So hydrolysis of nitriles to give carboxylic acid. Here, take any nitrile, take dilute acid, with heat, you will get this product here. Okay, another example, if you recall, take a cyanohydrin, which of course we could, this cyanohydrin we could obtain by reaction of hydrogen cyanide with an aldehyde. In this case, because we have an hydroxy group that could be dehydrated to form carbon-carbon double bond, we want to use a basic hydrolysis. So this time we say 1. The hydroxide could come from sodium hydroxide or potassium hydroxide. And then after you do the hydrolysis, then you acidify the solution with dilute acid. So now we get this here. Okay, let me give, before I give you a couple more examples of reactions of nitrile, let me give you the mechanism for this reaction. Okay, let me simply use a generic, nitrile, okay? Let us use a generic nitrile. Say we take this here. Say generic nitrile. If you take this, what happens, this nitrogen here, because nitrogen is more electronegative than carbon, it is drawing electron cloud away from carbon here. So we could think of this as having a partial negative charge, and this carbon here having a partial positive charge. In essence, the nitrile will be reacting just like a carbonyl group. So if you have You have a dilute acid. So what happens here, because we also have non-bonding pair of electrons here. What happens here, just as in the case, just as in the case of the carbonyl group, the non-bonding pair of electrons on nitrogen to grab the proton on the hydronium ion, and then you have this. So now this nitrogen is now positively charged, and is so doing, is making these carbons here, will be making this carbon here a lot more electronegative, because now this electron wants to now come to nitrogen right here. So what are you going to get? So we have this. Of course, you know we form water here. So this here, the water comes here acting as a nucleophile, attacks this, and this electron is put to nitrogen. And let me use a different color pen. So now you have this here. Okay. Now this non-bonding pair of electron on nitrogen will now come in. Once again, grab the, let me put the electron here to make it easy for us. Come in to grab this proton here, just as it did in this case, right? And then you release this pair of electron to oxygen, and therefore we have this. Okay. Okay, now this is an unstable intermediate. What will happen here? Another water molecule, I'll put that here. Will come in. Because of the positive charge on this here, the electron will be drawn towards the nitrogen, and then you simply have this attacking here, and this electron goes right here. So now we have this. Nitrogen is here. This is here. This is here. You have electron on nitrogen. Now you have, this is our green color here, and blue for the other water here. Okay. And now what is going to happen? What do you think will happen at this point? Nitrogen will, exactly. Nitrogen will grab the proton again. Very good. Okay, so now we have this here. So what do we have? We have this. And we have this. And all of these things happen very rapidly. So even though we are writing, it seems like slow, but they do happen very rapidly. Okay, now what happens at this point, we are now going to lose ammonia, because ammonia is a very, very stable molecule. We lose ammonia here. Break away. Okay. While it is breaking away, we are also going to generate a carbon-oxygen double bond. Okay. And so what we have here, we have this. And since ammonia is breaking away, and also in this, we are losing a proton here, ammonia and that proton will get together, and then you end up with ammonium ion. Okay? And so you could see here, that's how we go from the nitride to the carboxylic acid. So this reaction actually do happen. So anyway, I just thought I should let you have some idea what is going on here. Essentially, the carbon-nitrogen triple bond sometimes behaves as though behave very similarly to a carbon-oxygen double bond. Yes.
When ammonia breaks away from the bond, does the carbon become positive?
Yeah, you could do it in two steps. You could do it in two. I just did it in one step. Because it could become positive later, but it comes back and pick up the proton anyway. Okay. 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 So anyway. So that is the first reaction for nitride, which is the hydrolysis of nitride to give carboxylic acid. The second reaction, still on reactions of nitride. Second reaction, this you've seen this before. This is reaction with guanine to form a ketone. Okay, so you have a nitride. And you have a guanine reagent. Okay, this is step one, and then step two, you follow that up with hydrogen ion. This time you get a ketone. I will tell you the reaction mechanism is closely related to the one I've just given you. So to save ourselves some time, I will not give you the mechanism for this reaction at this point. So we get this. Okay, the point we made here is anytime you have a nitride and you react with a guanine reagent, you get a ketone. Okay. If you want another example, say this here. And we could use this as benzene magnesium bromide as a guanine reagent. Keep in mind you do step 1 and step 2, because if you don't do that, if you add both the dilute acid and grignard at the same time, what happens, the grignard will react with the dilute acid, and then your grignard will be destroyed. Okay? And there will be no reaction. That is not the reaction that you expect. Okay, so now you get this. Okay. So that's reaction number 2 for nitriles. Okay, the last reaction I will give you for nitrile. Nitrile will react with lithium aluminum hydride to give you a primary amine. Okay, reaction with LAH. All of you know what LAH means by now. To give a primary amine. Okay. If you take a grignard, if you take a nitrile, and you take lithium aluminum hydride, LAH, lithium aluminum hydride, and then you follow that up with hydronium ion. Keep in mind it has to be step 1 and step 2. You need to indicate those steps. Because if you normally take lithium aluminum hydride in the presence of dilute acid, this is what you get. All you get is hydrogen. Okay, hydrogen gas. Okay, so therefore all your lithium aluminum hydride will be destroyed. Plus lithium hydroxide, okay, and aluminum hydroxide. Okay. Okay, so therefore that is why you have to do step 1 and step 2. So okay, you do that, then you will get this. See what has happened here, this carbon here, the carbon of the nitrile is converted to a CH2 group, and of course the nitrogen here, we are adding 2 hydrogen to the nitrogen, okay? So we call this a primary amine, this class of compounds in which you have nitrogen attached to a carbon, and that nitrogen could be attached to either hydrogen or other carbon atoms. We call this amines, and because we have 2 hydrogen attached to this nitrogen here, we call this a primary amine. So when we get to chapter 24, we are going to discuss amine to greater detail. Okay, so anyway, you take a nitrile, lithium aluminum hydride, you get a primary amine. Okay, another example. LAH followed by hydronium ion. Okay, so we have finished the reactions of nitriles. I've given you 3 methods for with regard to reactions of nitriles. So now let us take a look at the reactions of carboxylic acid. First reaction, reaction with thionyl chloride to give what we call acid chloride. We will talk some more about acid chloride in the next chapter, which is chapter 21. So you take a carboxylic acid, this case, this particular example, benzoic acid, and you react with thionyl chloride, okay? We react with thionyl chloride. What happens, the thionyl chloride will replace the hydroxy of the carboxyl group. Remember, that is similar to, remember when we reacted the thionyl chloride with an alcohol, what do we get? Remember the thionyl chloride with alcohol? We get a chloride, exactly. So something similar is happening here. The difference here, we are dealing with a different molecule, so we call this an acid chloride, okay? In this case, benzoic chloride. Okay, but the general name for this class of compounds is acid chloride, in which you have a carbonyl is attached to chlorine atom, and that carbonyl is attached to a carbon atom. Okay. Another example. By the way, SO2 is formed here, and you don't have to worry about those. Okay, so you have okay. This case we form a proper chloride. Okay, so let us take a look at another reaction of carboxylic acid. That's reaction number 1. Have you guys done esterification in the lab? Those of you say, okay. Okay, esterification. So number 2, acid catalyzed esterification. Okay, using alcohol. If we take, okay, I know you did this, I know you took a benzoic acid, is that what you did? Okay, so let us give you that example. Take benzoic acid. This here, you do this in the presence of catalytic amount of acid. Okay, let us say we're using methanol, any alcohol. For the most part, we use low molecular weight alcohols because they are liquids. And then, you notice what I did there? I did not put hydronium ion because generally you do not want to have too much water in there because this is a reversible reaction. Look at this. Did they give you the mechanism for this in class? In the lab? Okay, so we don't need to do that here. Okay, good. Huh? You didn't? Okay, well, I will give you the mechanism in the next chapter because we are going to discuss this here some more anyway. So what happens? For methyl benzoate, this is an ester. And this type of reaction in which you take an alcohol and you react with a carboxylic acid to form an ester, we refer to this as Fischer esterification. Okay. Okay, this reaction here, generally you use an excess of methanol in order to drive the equilibrium to the right. I'm sure that's what you did in class. Because you use methanol as a solvent, you also use it as it's also the reagent. So in that case, the reaction will go mostly to the right, because any equilibrium reaction, you want to drive the reaction in one direction. So that is why you use excess of this. But in your case, you don't need to write excess for me. Okay, this is not a lab. Just write methanol, that's fine, or the alcohol. Okay, so anyway, this is another example of reaction of carboxylic acid. In this case, with methanol, with not methanol alone, with alcohols to give an ester. So we could, for example, we could do this. I could do that. Take this time we could use ethanol as the alcohol and then some acid as a catalyst. And then what do you get? You get ethyl ester of the corresponding acid. Okay, that would be the ethyl ester of that acid. Okay, so now let us take a look at another example of reaction of carboxylic acid. So far I've given you 2, 3. This is a new reaction to all of you. This is new. We call this Volhard Zielinski. This reaction was named after 3 scientists who discovered the reaction at the same time. Reaction. In this case, if you take a carboxylic acid, as long as the carboxylic acid has an alpha hydrogen, okay, this is the alpha carbon here. This carbon here is what we call alpha carbon. And the hydrogen that is attached to the alpha carbon is called alpha hydrogen. As long as you have an alpha hydrogen in that molecule, and you take this phosphorus tribromide in the presence of bromine, okay? So this is another reaction for phosphorus tribromide for you. You will get this. So what this reagent does with carboxylic acid is to replace one of the alpha hydrogen in the molecule with a bromine atom. So that is what it does. Another example, supposing I have this. If I have that, and I use that reagent, phosphorus tribromide in the presence of bromine, what is going to happen? This hydrogen here will be replaced by bromine, right here. Okay, I'm sorry, bromine. Okay, so that's the Volhard Zielinski reaction. You use this reagent here, bromine, phosphorus tribromide in the presence of bromine, and then you replace the alpha hydrogen with a bromine atom. Okay, so one more reaction of carboxylic acid before we go into working problems today. Oh, we have plenty of time. Okay. You like that? Okay. Reaction number 4. We are going to call this acid-base reaction. Okay. Of course, unlike most organic compounds, we call this class of compound carboxylic acids. We call them acid because they are acid, because they react as acid. Okay, so therefore acid-base reaction is very important to this class of compounds. For example, you take this. And you take sodium hydroxide, any kind of base, or potassium hydroxide. Okay, so the sodium hydroxide, essentially this here, will simply react in an acid-base reaction with the acid, and then what do you get? Hydroxide will pull up this here, this proton here, to form water. It's an acid-base reaction, and of course the sodium is simply just here somewhere to balance up the carboxylate. Okay, so we form in this case sodium carboxylate. Okay. Now, since acid-base reaction is very important with respect to carboxylic acid, different carboxylic acid will have different acidity. In other words, the different levels of acid strength. Let me see here. Okay. Let us take a look at this here. Remember, we did a pKa, sometime was it last semester. We use the pKa to measure the relative acidity of different organic compounds. Oh, by the way, for your hour assignment, you do not need to do those problems that has anything to do with pKa value or calculation of pKa value. Okay? That you do in analytical chemistry. Okay, so just omit those questions that has to do anything with pKa value in the hour assignment. Okay. There are two factors that will affect the acidity of an organic molecule. And those two factors, acid strength or acidity of organic compounds. One is resonance. And the other is inductive effect. Resonance and inductive effect. Let us say, for example, if I have this here, that's acetic acid. As you can see here, the pKa value for acetic acid is, let's say 5. Let's say 5, close to 5. And if we take ethyl alcohol, the pKa value for this is 16. And the pKa value for acetic acid, let's call it 5. Just round it off to 5. Keep in mind, the pKa value is a logarithm value. In other words, if you take a look, the difference in acidity between acetic acid and ethyl alcohol, that's a factor of about 9. So what does that tell us? That tells you that acetic acid is 10 to the 9 times stronger acid than ethanol. That's almost 1 trillion times stronger than ethanol as an acid. Okay? Okay. So how do we account for this? Generally, when you consider an acid, the strength of an acid depends on the stability or the weakness of this conjugate base. Let me write that down because that is very important. Strength or acidity of an acid depends on the stability or weakness, call it weakness, of the conjugate base okay, so let us take a look at this. Take a look at carboxylic acid, acetic acid. If we lose this proton here, to form this. Okay? What you obtain when you lose the proton from an acid is what you call the conjugate base. This is the conjugate base of acetic acid. So, conversely, relative to this conjugate base, we will say acetic acid is the conjugate acid of this base. Okay? Now, let us take a look at the conjugate base of ethanol. This is the conjugate base of ethanol. Therefore, with regard to this conjugate base, ethanol will be the conjugate acid. Okay? So what do we have here? Why is acetic acid more acidic than ethanol? It's because of resonance. The conjugate base is stabilized by resonance. Okay? The conjugate base is stabilized by resonance. Therefore, it is more stable than the conjugate base from the ethanol, because you cannot stabilize it by resonance. Another way to put it is that the conjugate base of acetic acid is weaker than the conjugate base of ethanol. Okay? So therefore, you guys know how to write the resonance for this, right? We could write resonance for this. Take this out. This could be stabilized by resonance, in which you simply move this pi electron to here, this goes to here. So this electron pair here is being shared by these three atoms. Okay, and that stabilizes that conjugate base. So what do we do? Simply moving this to here and this to here. But we cannot do that with ethanol. And that is why acetic acid is a stronger acid than ethanol, because the conjugate base is stabilized by resonance. So I told you there are two factors that will stabilize the conjugate base. Okay? Now, let us now come back to this chart here. Yes. Okay. Now, with respect to inductive effect, okay, I've just told you how the resonance will stabilize our conjugate base. With regard to inductive effect, take a look at these molecules here. Let me go ahead and take this off. Let us label this. Let's call this A. That's acetic acid. Let us call this B. This is C. And this is D. If you look at this, what is the difference between all of this here? In acetic acid, the alpha hydrogen, all of the alpha hydrogen are still here. Now, when we replace one of the alpha hydrogen with chlorine, look at what happened to the pKa value. It goes down. In other words, this here is more acidic than acetic acid. When you replace with two hydrogen atoms, what happens? Look at the pKa value. These are experimental data that you could actually go in the lab and you could determine these values. Okay? So therefore, look at what happened. The pKa value goes down. Then when we replace all of the hydrogen with chlorine, pKa value goes even further. So what is the explanation for that? And the explanation for that is that when you form the conjugate base, in this case, when you form the conjugate base, let's put the chlorine here. The chlorine here, being electronegative, is able to draw the electron cloud to, in other words, inductive effect. Maybe I need to define that again. Inductive effect is the ability to draw electron cloud from one part of a molecule to another part of the molecule. In other words, help in sharing the negative charge. Okay, the ability to draw electron cloud from one part of a molecule to another part of the molecule. Electron cloud from one part of a molecule to another part. So generally, molecules do not want to have an atom that is simply only taking care of a negative charge. You want to distribute those negative charges over the set of atoms within this given molecule. So here, what we have, because of greater electronegativity, okay, so you have the dipole moment towards here. So the chlorine is drawing electron cloud towards this direction. In other words, this negative charge that is here, if you have chlorine here, chlorine will be drawing it to the air. And that is what we mean by inductive effect. So therefore, the more chlorine or the more electronegative atom that you have within the molecule, the more stable the conjugate base will be. Okay? Okay, and that is what you see here. Okay, now let us take a look at this one here, this set of data here. Here we have essentially the same type of acid. All of these are butanoic acid. Look at what we did here. We replaced the hydrogen on this carbon with chlorine. pKa value is this. Then we replace the hydrogen on this carbon here. Let us number those carbons. This is carbon 1, 2, 3, and 4. Okay, when you replace with the hydrogen on carbon number 4, look at the pKa value. When we replace the hydrogen on carbon number 3, we are now getting closer to the negative charge of the conjugate base. Keep in mind, you remove this here to form a conjugate base. So we are talking of stability, stabilizing the conjugate base, not the acid itself. Okay, in this particular instance, let me take this out. Keep in mind, when we talk about stability, we are referring to the conjugate base. So here, let us say here, the conjugate base would be this here. Okay. So we replace one hydrogen here, the hydrogen with chlorine. What do you have? That is what we have here. pKa is 4.2. And when we replace the hydrogen on carbon number 3, look at what we have. pKa is going down. In other words, the closer the electron withdrawing group is to the carboxyl group, the lower the pKa. That as this hydrogen is becoming more acidic. Okay, when we replace the hydrogen on carbon number 2, see it even goes down further. Okay, so therefore, if I give you, if you are given a set of molecules, you say, okay, which is the most acidic? If I give you this molecule here, which is the most acidic? Okay, all that is in the acidity on the based on the pKa value, which is the most acidic, going from most acidic to least acidic. You should be able to do that. Okay, giving the information we have just given you. So anyway, and so that is all we want to discuss about acid-base reaction of carboxylic acid. Okay, now I want to do some problems. Now all of these things we have been giving you, we're giving you a whole bunch of reactions. The whole essence of giving you reactions, so you are able to apply those reactions. Okay, we are not just giving you reactions just for the sake of it. So therefore, what I want to do now, let us now begin to put together all of these reactions we have given you, use them in some meaningful applications. Okay. Okay, Theophil, can you read this for us?
How would you make ibuprofen from ibuprofen?
Okay, very good, and thank you. Now, how will you make ibuprofen? How many of you have heard of ibuprofen before? Okay, you use that, or you use it as it's a very good painkiller, right? Okay, sometimes it is also called Advil, depending on who's making it. Okay, sometimes it's called Motrin. So when you see all of these, this is the same molecule. Okay, it's called ibuprofen, Advil, or Motrin. Anyway, how do we make this? Let us now begin to put together the knowledge that you guys have gained over starting from last semester, because we now have to begin to think of our final exam, because all of these things we have to put together as a comprehensive unit. Okay, how will you go from here to here? Okay, fortunately, you already have this group here. You have this group already here, so you don't need to worry about this. So what you need to do now is to make this part of the molecule. Okay? So the question that should come to your mind is, of course, we need to make a new carbon-carbon bond right here, right? That's obvious. And if you take a look at what we have to do here, we need to introduce 3 carbon atoms. So this is the kind of thing that should be going through your mind. You need to introduce 3 carbon atoms. This is 1, 2, and 3. You don't have to introduce all of this at the same time. Okay, anybody has an idea? How do we approach this? We want to form this carboxylic acid. Okay, using all of everything that we've done so far. Not just this chapter now. Okay, so what do you want to start with? Acylation? Okay, very good. You want to start with acylation. Okay, let's do that. That's good. So you want to start with Friedel-Crafts acylation. Okay. Okay, I'm assuming that you want to use this here. So we say we take this. So you want to use an acid chloride. How do you get that acid chloride? How do you get the acid chloride? Acetic acid reacting with thionyl chloride, right? We just did that. Okay? Okay. Okay, so now, okay, this group here is an auto-para director, so we want to place this in the para position. Very good. Okay. Okay, so we've done the acylation. Now, what do you want to do after that? Okay, so you now have 2 carbons here. You need 1 more carbon. You need 1 more carbon. Okay. Grignard? Okay. Okay, well, let's try that. Now, I wasn't thinking Grignard, but let's try that. That might work. I guess I'm assuming that you want to use that Grignard, right? Methyl Grignard, right? Okay. Step 1 and step 2. Okay, and that will give you this here. Okay, that will give you this here, and this here. Is that right? Linear reaction with a ketone to give you a tertiary alcohol. Is that right? Okay. What is the next one? That's a good one. Well, that wasn't what I wanted to do, but that's fine. Okay, what's the next step? Keep in mind, eventually we want to form a carboxylic acid. Dehydration, okay? You want to do dehydration. What do you want to use for dehydration? Dilute acid or phosphorus trichloride, right? You could do that. And that will give you this. Actually, I wanted to get to here, but what I wanted to use was a Wittig. Right? You remember Wittig? Okay, I wanted to use a Wittig. That's one step, okay? Because instead of 2 steps, okay, but this is fine, okay. Okay, now you found this. Now what do you want to do with this? Huh? What do you want to, which one? I didn't hear you. Addition? Keep in mind you want to end up getting to here. Okay, you want to do boration, oxidation. You want to make an alcohol. Because you could make carboxylic acid from a primary alcohol, right? Okay, so what do you want to do? BH3, or which kind of addition do you want to do? Anti-Markovnikov, right? Exactly. So you want to do anti-Markovnikov addition of water. Step 1, borane, followed by step 2, hydrogen peroxide in basic medium. So that gives you this. That's it. So that gives you that, right? So now you form your primary alcohol. Then from the primary alcohol, what do? You oxidize the primary alcohol. It's chromium trioxide in basic medium. I'm sorry, in sulfuric acid. Okay? And that gives you the ibuprofen. Now, supposing I ask you to do this from benzene, just for an exercise. Well, okay, now we already know how to do this part here. Supposing I ask you to do this from benzene, in other words, the isobutyl benzene, you have to make it. Okay, let us see. You got it down? Can I go to the next page? Okay. Okay, supposing I say make ibuprofen from benzene. Okay, keeping in mind that we've already done this part here, so we now need to worry about how do we make this. In other words, how do we make this from benzene? That's what that amounts to. Okay, so the question is going from here to here. Okay, eventually we want to go to here. We've already done this part. Okay, that's your ibuprofen. This is already done, so we don't need to worry about this. Okay, how do we do this? What is the approach you want to use here? We have alkylation. What? Say that? Huh? Did you say alkylation? Okay. Alkylation using what? What alkylating agent? Which alkylating agent you want to use? Okay. Which alkylating agent you want to use? Okay. Now keep in mind that if you I know some of you might be thinking, why don't you use this, right? Right, or the chloride in the presence of. If you do that, keep in mind you are going to get this here. Because you remember during alkylation, you form a carbocation. And the carbocation will rearrange to form the more stable carbocation. So essentially what you are going to get will be this here. What alkylation will give you will be this. If you do that. Because what happens, once you form the, keep in mind, in the presence of the aluminum chloride, if you recall, when we did a fiddle cap alkylation, the first thing that you get here will be this here. Once you lose this bromine, okay, that is the intermediate, that is the electrophile you are going to form. And that electrophile will rearrange as a result of alkyl shift, a proton shift to a more stable carbocation. So that will not work. And therefore you get this to become this here. And this will be your electrophile that will react with the benzene to give this here. Okay? So this will not work. Okay, so, well, let's save some time here. You want me to help you out? Okay. Well, let's start. Okay, how many carbons do we want here? We want to introduce this carbon here. 1, 2, 3, 4, right? Okay. Let us start with one carbon at a time. We know there is no rearrangement on that carbon. You are right, we need to do our alkylation. Okay, but the question is, what is the alkylating agent? Well, since this is almost like a review at this point, so let us hopefully just play around with this here. So we could start with fiddle cap alkylation using methyl chloride in the presence of aluminum chloride, right? And then you get that, okay? Keeping in mind now that what I want to do now, I want to functionalize this carbon here. So I will say I want to react that with MBS. What would that give us? The MBS will bromine will replace the hydrogen on a this here we call it benzylic hydrogen here. This is a benzylic hydrogen right here, benzylic. If you recall, benzylic hydrogens. Okay, the MBS will replace any one of those. So we get this. Okay. Now, what do you think we want to do with this? Keep in mind, this is where we want to go. Now, we've added this carbon now. We need 3 more carbons to go. What I will then do, I will convert this to a Grignard, right? Step 1. Magnesium is ether. And then I will introduce a ketone. What kind of ketone will I use here? Acetone, right? And then step 3, we add dilute acid. So now I get this. Okay, so I get that. And then what do you think? Keep in mind, this is where I want to go here. So what do you think I do now? Dehydration. Okay. I do dehydration with what? Phosphorus oxychloride, right? Okay. Hopefully this is review for all of you. Or dilute acid. And that gives us, you could get a double bond here, it really doesn't matter, right? Okay, so that will give us this here. So let me put it on this side. No. Get a double bond here, CH2, CH3 here, and then finally I take this alkene here. What do I do with that? Hydrogenation, right? Very good. In other words, the reason why we're giving you all of those reagents and reactions, so you could put this together in a synthetic application. That is the essence of organic chemistry. Okay? The first part, like I keep telling you, the first part is pure memorization. Then this part is where you actually have to think. Okay. Okay. One more problem. Oh, time is gone. Anyway, this is a problem I wanted to share with you. You may want to think about that. Okay, that's the one we did, okay. This one here. Okay, Kiara, can you read this for us? We got 2 more minutes.
Depakote is a drug used in the treatment of epilepsy and bipolar disorder. Its systematic name is 2-propylpentanoic acid.
Okay.
Five a synthetic scheme starting with fluorhexamine.
Okay, so this is what they wanted to do. They wanted to start with 4-heptanone. Everybody should be able to do this very easy. It's another pharmaceutical drug. And they wanted to make 2 Depakote, which is 2-propylpentanoic acid, which is essentially this here. Propylpentanoic acid, okay. One, 2, 3, 4, 5. So 2-propyl. Okay. Now this is very easy to make. Okay, 2-propylpentanoic acid. If you look at this here, this part of the molecule, if you look at this, it's essentially could be all of this here. So what does that tell us? You need to form a new carbon-carbon bond right here on this carbonyl. Okay, you need to form a new carbon-carbon bond. So how do you do that? You could use Wittig, you could use Grignard, right? Supposing we use our Wittig. Sometimes we use this to represent benzene, okay? So triphenylbenzene, this is a Wittig reagent. If you do that, then we'll get this. Then what do you do after this? Boration, right? Do boration. Okay. Hydration. And that will give us that will give us that primary alcohol. And then of course you then oxidize the primary alcohol with chromium trioxide. Okay, the point here is, those reagents or reactions will give you the ultimate goal of this reaction is for you to be able to use them in applications. Okay, anyway, so when we come back on Tuesday, we will finish up on that. Well, I'm almost through with chapter 10. So there's one more thing I want to share with you, but we'll do that on Tuesday, and then we'll start with chapter 21. And also there will be a short quiz on Tuesday based on what we've done so far in chapter 20. Okay, so enjoy your weekend, and I will see you next week.